So welcome to lecture number 4 of the quantum mechanics course. Today we talk about projectors, bras, and kets. And projectors play a key role in quantum theory. And in fact, we already saw that in the axioms. And they deserve to be studied in detail, and today we'll do that. And essentially, this is very cheap linear algebra up to the subtlety that we may deal with infinite dimensional subspaces, and there is a little subtlety we have to take care of there. So most of the first part of today's lecture will be rather trivial, up to 1 or 2 points, which I would like to draw your attention to. That's the first topic of the lecture. The second topic of the lecture are the so-called bras and kets. So that's the Dirac bra and ket notation. And their definition is very clear and is based on the so-called Riesz lemma that we're going to prove. Riesz. Like this, on the Riesz lemma. Their use in quantum mechanics is very intuitive. And that's the reason why people like it, because you can write projectors using the bra-ket notation in irresistibly charming, simple form. Well, while their use is intuitive, its definition, the definition of that use, is rather cumbersome. So if you really want to say how to use them, then you have to invent all kinds of extra rules of how you deal with it and what you really mean by it. And at the end of the day, all of this is already in our standard notation without inventing lots of of extra rules. So we will not use that notation. So apart from an initial charm it carries, it only causes trouble and misunderstanding and wrong intuitive conclusions and all of that. We'll not use that notation, but obviously I introduce it because the textbooks are covered with this stuff. And of course, people informally talk using the bras and kets, but you will always want to translate this into proper notation. And then you say, oh, is that what you mean? Oh, now I understand. Okay. Or if that's what you mean, well, then I don't understand. Okay. So we have a fully developed notation. We don't need extra notation with hidden rules. Okay. As intuitive as they may seem. So we first start with projections and Pythagoras' theorem. Now, obviously, in finite dimensional Hilbert spaces, vector spaces, there's not much to be said. Nevertheless, we will consider a separable Hilbert space. So let H be a separable Hilbert space. Should I ever in the future fail to mention separable, I meant to say it. Let H be a separable Hilbert space with the appropriate structure on it. Then we have the following definition, very simple definition. Let psi in H be, let psi be in H, then and E in H a unit vector, meaning, of course, that the norm is 1. Then we define psi parallel, namely parallel to E, as that part of psi which you obtain by projection to E in this fashion. So that's just a definition. It's called the projection of psi to E. That's very simple. And whatever is left, so if you subtract from psi this projected part, you call the orthogonal complement. Okay, so this is really very simple. Now here maybe it's important to note the order. The psi comes second, so that this projection map taking psi to psi parallel is linear. If the psi was in the first slot, it would be antilinear, right? So please keep the order in mind. Okay, so now this is very simple. This is for one vector, and it's interesting to understand this for an entire, well, at most countable set of orthogonal vectors E. It's interesting to understand the extension of this elementary, or these elementary definitions to at most countable sets EI, where the I comes from an at most countable set, capital I. And obviously, if we're dealing with a separable Hilbert space, this orthonormal countable set may well be its basis. So this definition comes in the form of a proposition, because one cannot simply define here. One needs to prove that all the limits exist. So a proposition, again, let psi be in H, and let the EIs with I from some I be an orthonormal set in H, so not necessarily a basis yet, for an at most countable set, index set I. Then we have that A, well, you can still decompose psi, or you can decompose psi as psi orthogonal plus psi parallel, where the psi parallel is defined as the sum of over all the I in I of projecting the psi to the ith element of this ON set times EI. And you say, well, this is simple enough. Why is this not just a definition? Because it comes in form of a definition. Well, here again you have this to be psi minus psi parallel. Well, the question is, if I is countable and not finite, does this limit exist? It could simply be that I choose such a set, but this limit simply does not exist, right? I need to check. Hence, the whole thing is a proposition rather than a definition, okay? And that's something also to be proven. If you take the psi orthogonal and you take the bracket with the jth basis element, not basis, element from this orthonormal set, then you get 0. So this needs to be shown. Then B, we have Pythagoras theorem. Pythagoras holds. How does it look like? Well, it says that if you take the psi norm squared, that is the norm squared of the orthogonal complement, plus the sum I in I of all possible absolute values squared, EI psi, like this. And that's obviously Pythagoras' theorem, but now we could have countably many summons. So it's a little more than Pythagoras' theorem extended to d dimensions. It's Pythagoras' theorem extended to countably, well, to infinite dimension on a separable Hilbert space. Now, moreover, there is a useful characterization of the parallel component of the projection to this set E. So that's the third part of this proposition. For any gamma that lies in the span of all the EIs, you remember that the span is the set of all finite linear combinations of such vectors. Although these may be countably many, the span is the set of all possible finite linear combinations. For any gamma in the span of the EI, and let me just draw a finite dimensional picture in order to see what is meant here. So if this is E1 and E2, but the point is that this holds for infinitely many EIs. If I have two E's and say I'm in a three-dimensional space in total, okay, and then I can look at a particular vector psi, as we usually do, and you can consider the projection of this psi down here into this span, okay? But now imagine you consider an arbitrary gamma in the span. So an arbitrary gamma in the span may be that guy. You agree? That lies in the span. That's the psi, and the red guy here is what we usually call psi parallel, right? That is the projection into there. And if you want to complete the picture, although we don't really need this at this point, then this guy here would be psi orthogonal. Okay? So that's the situation. You have the psi, you have the projection into this span, that's the psi parallel defined here, and you have an arbitrary gamma. Now, the claim is for any gamma in the span, we have the estimate that psi minus the gamma, so that's in a sense the distance of the psi from the gamma, so that's, well, lacking colors here. Let's take red again. Now let's take white. So that's this one here, psi minus gamma is this vector here, right? Psi minus gamma is this one here. And now compare the length in this intuitive picture of this one to the length of this psi orthogonal. And then you see, this is always greater or equal to psi orthogonal length. Right? So this psi, not orthogonal, psi parallel. Psi parallel is the one vector, the unique vector in the span that is closest to this psi, because equality holds if and only if the gamma coincides with the psi parallel. So that's the idea. That's the picture. But of course, the picture is here drawn for 3 dimensions to aid memorizing this. But of course, the claim is here that this is true for an arbitrary, at most countable index set. Okay? So let's prove the whole thing. Let's start in the beginning. And, well, actually, the proof is extremely simple because at first, assume I is finite. And then, of course, we may assume that I just goes up to some number n. That's the index set. And then the whole thing is really very elementary linear algebra. We very quickly go through this. So these two guys are actually definitions it is clear from these two definitions that this one holds. So this is a definition, this is a definition. Because of the second definition, well, the second definition is just this claim, so nothing has happened, okay? Nothing has happened if this is a finite sum, because then I know it converges. Well, it's a sum. It's well defined. The only thing one has to check is this guy here. Well, yeah, that's not too tricky. So let's plug that in. We use the definition from here. It's psi minus psi parallel, but the psi parallel is I equals 1 to n. It's a finite sum of the ei comma psi ei, and that's in a bracket with an ej, and the j is arbitrary from I. Okay, so, well, now it's just an application of the rules here. I can, of course, this is a finite sum. I can pull this apart. I can do all possible kinds of things. I could write psi comma ej minus. Now I pull the sum out as I equals 1 to n. Well, I pull this guy out. Remember that because this is in the first slot, pulling out a scalar requires that the scalar gets a bar, right? Because the product is antilinear in the first slot. So you pull that one out, and then you have an ei comma an ej. Well, then we assume that you have an orthonormal set. So with this funny symbol delta ij, you see that the sum only flips, only has a contribution if the I is a j. Then you can use the property of the inner product that this actually equals psi comma ei bracket like this. Ei like this with this delta ij. The whole thing is 0. This is what you wanted to show because this one is the psi orthogonal. Okay, so I mean this is really very, very elementary if the I is finite. Well, similarly, I'm not going to do that. Similarly, prove Pythagoras for finite index set I. Okay. In the future, if things are that simple, I will not show them, but here I'll do that for a certain purpose, you'll see in a second. So finally, the C part, well, we just start evaluating psi minus gamma. Now the gamma is supposed to be in the span of the EIs. That means there exist coefficients gamma I such if I go over finitely many, I have finitely many coefficients, I can expand this in, since gamma is in the span of the EI by assumption, right? So I can write this as psi orthogonal plus psi parallel because of step A minus this gamma. But that amounts to, if you look at this, this is psi orthogonal plus the sum. Well, the psi parallel goes from 1 to n ei psi ei minus, now I put them all under the same sum. I can certainly do this because it's a finite sum. Otherwise, I might worry about ordering ambiguities. Something like this here. Then the norm closes. Well, distribute at will squares here. And then you use Pythagoras that we have just shown. You know that everything that has an expansion in EIs is in the parallel complement, is in the parallel part. So this is this plus the sum of each individual contribution. It's the EI psi minus gamma I absolute value squared. And this is from 1 to n. And because these are all non-negative, we have the estimate as claimed. But all of this only for finite index sets. Now, we need to extend the results to I countable. So that's the essential step. So you see the finite case, well, this finite sums, that's child's play. But what happens if you go now to countable? Well, you know what you need to show based on the finite formulae. By finite, I mean for finite index sets. We need to show that all limits exist. Because you can show all these formulae and then you just showed them for the partial sums, so to speak. So you definitely need to do this in a finite case. You need to do these finite calculations. But once you did them, you just see whether all the limits exist. So here, the only thing you need to check is whether this limit here exists, whether you need to check whether I equals 1 to n, these partial sums over ei psi ei. You need to check whether the limit n to infinity exists. Because this limit is exactly what we defined as psi parallel, right? We wrote psi parallel is the sum over all I in capital I of this thing. So does this limit exist? Well, when do we know whether a sequence, so this is the sequence of partial sums, we know a sequence converges if it satisfies the criterion for convergence. However, this is a sequence of partial sums in our Hilbert space, right? It's a sequence in a Hilbert space. So do I need to show convergence, or is it sufficient to show that this is a Cauchy sequence? Well, of course, it suffices to show that these partial sums are a Cauchy sequence. Why? Well, because the Hilbert space is complete. I know if it's a Cauchy sequence, it certainly converges. So you see now, so far we had to prove something is complete, but now we're starting using it, right? Okay, so we need to show where this is a Cauchy sequence. So it suffices to show that this sequence of partial sums is Cauchy. Yes?
Could you maybe lift at least the blackboard where you don't need them anymore because you lift your blackboard and then lift the old one? So we could maybe see it from the backwards. So because it's quite hard to read the last line here.
Okay, so, well, you see, okay, so I can go up to here for the camera. I don't want to move the blackboard all the time. Because in the last row you can get up and get a better angle.
Okay.
Also follows by this part C of the theorem. Okay, so, well, just consider the following estimate. We need to check it's a Cauchy sequence, right? So just check what happens to if you start with I at some m and you go up to some n. So take n greater or equal to m and check what you know about this guy. What do we know about it? From what we already derived so far. Well, we know that this is I equals m to n of the absolute value of ei psi absolute value squared. Right? This is Pythagoras. There's no orthogonal part here. And we know that this guy here is less or equal than the norm of psi. Well, this is also Pythagoras, right? Okay. Well, but that means so psi is, for any fixed psi, this is a number. So this is a bounded sequence. So from this we conclude this sequence is bounded. From the fact that it has only non-negative summons, we know that it's increasing. It's monotonic. Monotonically. So it's bounded from above, if you want to be very precise. And it's monotonically increasing. What do we know about a sequence that's monotonically increasing and bounded from above? It converges. Okay? That's right. If it converges, it is certainly Cauchy. Because any convergent series is Cauchy. But if this is Cauchy, this sequence is Cauchy, then this sequence in here is Cauchy. Hence the sum I equals m to n, ei psi ei is Cauchy. Hence it converges. Hence psi parallel, as defined in the theorem, is indeed an element of the Hilbert space. That's it. That's it. So you see, you really only have to do the stuff one usually does, and there's only a very small extra argument that you have to provide in order to check whether your infinite sum really is an element of the space where you claim it is an element of. Okay? So very often, again, proofs in the separable Hilbert space case that's infinite dimensional only require a little extra work, but that extra work is required in order to make the theorem true, rather than maybe falling into the trap of stating something that's only true in the finite dimensional case. And only very few quantum systems that we actually want to look at in physics would then be treatable. So that would be a nice exam question, right? Show this and that, and you'll be very careful to not only check the finite case, but to check existence of limits. Okay, so now we look at the relevance of closed linear subspaces of a Hilbert space H. Now, our theorems will very often say something about this set is closed and there's the closure of this set and so on. And that's a little, well, maybe at first puzzling why closure or topological closure comes into the game. And what is the relevance of closed linear subspaces? Well, it's this. Not any linear subspace, let's call it M of H. What is a linear subspace? A subspace is a subset, but a linear subspace is one where for all elements m1, m2 in the linear subspace, and for any complex number, it's true that if m1 and m2 are in the subspace, that m1 plus, and that's the plus on the Hilbert space, lambda times, that's the times on the Hilbert space, right? That this linear combination is again in the subspace. So it's a sub-vector space. A linear subspace is a sub-vector space. Not any linear subspace M and H, that is sub-vector space, is a sub-Hilbert space, which you might have assumed, because, well, a Hilbert space has more structure than a vector space, has also an inner product, and needs to be complete with respect to that inner product. For it may fail, so this M may fail to be complete. So this is the problem of just taking a sub-vector space. And we have a little lemma from topology, which we're going to prove in order not to confine this to mystery. Lemma, a closed subset. So you see now we're no longer looking, the linearity is not important at the moment. A closed subset M H of a complete space is again complete. So in order to preserve the completeness property, we cannot take any old subvector space. We need to take a topologically closed subset. Okay? And the topology we're talking about is, of course, the topology on H, which is the soft ball, open ball standard topology induced by the norm. Okay? Proof. How can we see this? It's quite instructive to see this. Well, we want to show that a closed subset M is complete if it's a subset of a complete space. What do we need to do? We need to consider a Cauchy sequence let's call it psi n. In the subspace. If we are able to show that this Cauchy sequence converges in the subspace so that it has a limit that lies in the subspace, then the subspace is complete, right? So if one says a Cauchy sequence converges, well, in the space whose completeness we want to show, okay? Consider a Cauchy sequence. We need to show that limit psi n to infinity exists and is an element of the subspace. It's not enough if it exists somewhere, it needs to exist in M. Now, since the sequence psi n is a sequence in M, it's certainly a sequence in H, right? So it's a Cauchy sequence in H, in the ambient space H. Hence, it converges in H. So we know that the limit n to infinity psi n exists, but we know only that it exists in H. Right? It exists, the limit exists in H. The question is, does it not only lie in H, but does it even lie in the subset M of H, in this subset of which all its members come from? But does the limit also lie in there? Okay? Well, if that is true, now, since M is closed, so now we're going to use the closure condition, a closed subset M. What does it mean for M to be closed? You tell me? M is closed. Topologically, what's the condition for M being closed?
H without M is open.
That's right. H without M is in the topology induced, the standard topology induced on H. Since M is closed, H without M in O is open, right? That's true. Now suppose we make an assumption which we're going to reduce to a contradiction. Okay? Now suppose the limit psi, the limit of psi n, is not an element of M. So let's assume it is simply not true that it lies in M, which would mean our theorem is wrong. So it's proved by contradiction. Now suppose the limit is not in M. Well, because H without M is open, then there exists an open set U in H without M that contains the limit right? Because if H without M is open and I have a point that's not in M, therefore the limit is an element in H without M. If that is open around every point of an open set, you find an open set that lies entirely within there, right? But then there exists an n in the integers such that for all n greater or equal to n, the nth element of the sequence lies in that open set, because it's an open set around the limit point. The sequence converges in H, the limit point lies in H, even in H without M. If you now know, if you know that's an open set around the limit point, then from a certain sequence member onwards, all sequence members must lie in this open set. Okay? But this U lies in H without M. And at the same time, the psi n all lie in M. Why? Well, because the psi n was a Cauchy sequence in M. So it cannot be true that they all lie in M, and from a certain member onwards, they do not lie in M. Contradiction. Hence, our assumption is wrong. Hence, is false. So hence, the limit n to infinity psi n is in M. But that is what we wanted to show. So the Cauchy sequence in M, any Cauchy sequence in M, because we made no special assumption as to what Cauchy sequence this is, converges in M. That's it. It's a very simple topological fact based only on the definition of closed subset and the definition of convergence with respect to a topology. Okay? So all is fine if in addition we require this linear subspace to be a closed linear subspace in the sense of topology, namely that its complement is open. So corollary from this simple fact, a closed vector subspace or linear subspace, it's the same, it's just different terminology for the same thing. A closed linear subspace M in H is a sub-Hilbert space. Of course, with the inner product induced from H. You just use the same inner product, but you only apply it to the elements of M. And additionally, if H is separable, which you might have assumed, I mean in this theorem anyway, yeah, you can assume this, I just emphasize it. If H is separable, then also M is separable. Obviously it is. You can find a subbasis. Okay? So now you understand why in many places we talk about closed subsets, or we're interested, if we construct something, we're interested in checking whether the result of the construction is a closed subset. Because if it's then also a linear subset, we know, we have a sub-Hilbert space. Why is it so great to have a sub-Hilbert space? Well, for instance, you know you can choose an orthonormal basis on it, right? Otherwise, you have no justification. You know that a separable Hilbert space has an orthonormal basis. But if it wasn't a separable Hilbert space, you had no justification assuming so. So certain constructions you couldn't do. By the way, the converse does not hold. So it's not true that only closed subspaces can be sub-Hilbert spaces, but that virtually never arises in practice. Okay. So let's immediately proceed to orthogonal projections. So again, if you have a thirst for physics, I assure you projections are all you need, or essentially what you need to extract predictions from your calculations in quantum mechanics, right? To extract expectation values and things of that sort. So it's very, very important to study this. So now we extend this whole thing to the following construction. So definition, let M in H be a, in brackets, not necessarily closed, so we will not assume this from the beginning, not necessarily closed, however linear subspace of H. Okay? So you know, okay, it's a linear subspace, but it may not be a sub-Hilbert space. So definition is then the set M orthogonal, which is defined as the collection of all elements in the Hilbert space, such that for all M in M, M psi, or mu psi, let's call this mu, for all mu in M, mu psi equals 0, then the set M orthogonal is called the orthogonal complement of M in H. Property or properties. M orthogonal is a closed linear subspace of M of H. So although the set M we started from, although the set M we look at, whose orthogonal complement we consider, may not be a closed subset, once you take the orthogonal complement is a closed linear subspace. Okay, so that's great. So we know the orthogonal complement of a linear subspace is certainly a sub-Hilbert space. Let's see why this is true. Well, let's first check that M dual is a linear subspace. Well, this is very simple because let's take M1 and M2 in M orthogonal. No, let's take psi 1 and psi 2 in M orthogonal, right? Then due to the linearity of the inner product, in its second slot, However, this is not so relevant here because you have a 0 here. So if I had defined the psi in the first slot, you could switch it anyway, and then the complex conjugate of 0 is 0. Okay, but in its second slot, psi 1 plus psi 2 is also in the complement, and also lambda times psi 1 is an element of the complement for all lambda in the complex numbers. So that's trivial because this inner product is linear in its second slot. Okay. Well, it remains to show closure. To show that M orthogonal is closed. Well, the first thing we note is that M orthogonal is the intersection over all mu in M of the pre-image of the 0 in the complex numbers under maps omega mu. I'll say a word about this in a second, where the omega mu maps, right, so the mu comes from M, is a map from H to the complex numbers that assigns to each alpha in H, it assigns the complex number mu alpha. So why is this true? Well, the M orthogonal, as you see from here, is all the psi's such that, is each psi such that for all mu, this condition is satisfied. Well, this condition is that omega mu of psi is 0. Is that right? So maybe to make this clearer, I call this, instead of alpha, I call this psi. So this is this 0, and one map picks a particular mu. But the M orthogonal is all the psi's where this is true for all the mu. So it's the intersection of all those sets, and the pre-image of omega mu of the 0 is exactly this condition that the psi belongs in here. Okay? So this is just by definition, this is just a rewriting of the definition of M orthogonal. Nothing more, nothing less. Okay? Now, whenever you deal with topology and you deal with unions and intersections, you know that the union, an arbitrary union of open sets is open, but only a finite intersection of open sets is open. However, we want to show that this is closed, and if we could show that each individual pre-image for a fixed mu was a closed set, then we know arbitrary intersections of closed sets are again closed. Okay, so we would already be there if we would already be able to show that this is closed if we only knew that this is closed for every mu in M, because then an arbitrary intersection of closed sets is closed. Okay, so this is why it's clever to rewrite it like this. It remains to show that M orthogonal is closed. It suffices to show that for each mu in M, the pre-image of the map omega mu of the set containing only the complex 0 is closed. Okay? So consider this set is a subset of the Hilbert space, right? Because the map goes from H to C. So we consider the entire Hilbert space without this pre-image omega mu of the complex set containing complex 0. Obviously, we want to show that this is open. If we can show that this is open, we show that this is closed. What is this? This is the set of all the psi in H for which the condition that qualifies you to be in here is not true. Well, such that for all, no, not for all mu, there's no all mu, we have a fixed mu, such that mu comma psi is not 0. Right? Because we take the complement. If we didn't have the complement, it would be those where it is 0. This is where it's not 0. Well, but this can be rewritten psi in H such that mu psi is an element of any complex the set of any complex number without 0. It can lie anywhere but there. And this here is, of course, omega mu of psi. But hence, this is the pre-image of omega mu of C without the 0, by the definition of the pre-image. Aha. Well, but we know that this here is open because the one element set is closed in the standard topology on C. So this complement is open in the standard topology on C, which we're of course always employing on C. But now omega mu, being just the map that takes a psi to mu psi, this is the inner product, and the inner product is continuous in the second slot. Thus omega mu is continuous. Thus we know here that the pre-image of an open set with respect to a continuous map is open because of continuity. Hence we know this is open in the topology on H. Since this is continuous, and this continuity goes into here. Done. Thus we showed that any such pre-image omega mu of the 0 is closed, and here we have an arbitrary intersection of closed subsets. Well, that is closed. That was our claim. Any questions? Well, if that's not the case, let's have a 7-minute break till past, and we continue. So let's continue. So definition. The map P taking H down to M that sends psi to psi parallel, where the psi parallel is defined by the set M here. Let me see, do I need a closed set? I think I want a closed set. Yes, so H to M, and let this be a closed linear subspace. So now I do no longer allow M to be just any linear subspace. Now I want M itself to be a closed linear subspace. If it's a closed linear subspace, it's a sub-Hilbert space. That means there exists an ON basis for the M itself. Agree? Because it's a Hilbert space. So there is a separable Hilbert space. So there's an ON basis for M. And then this parallel is defined with respect to this ON basis. Remember, we defined the psi parallel as this sum. I in I, where I is now the space, could be the spaces, EI, psi, EI of M. So this map P is called the orthogonal projector to the sub-Hilbert space M. And now you see, if this wasn't closed, you understand now this closure criterion. If it wasn't closed, you were not guaranteed that you have an ON basis, then you wouldn't know how to define the psi parallel in the first place. Okay? It's called the orthogonal projector to the sub-Hilbert space M. It has the following properties. And let's call this map P down M, because it obviously depends on the choice of M. The first property is that if you take Pm and you execute it after itself again, you still obtain the same map. And sometimes this is written Pm squared is Pm. Of course, the square is here the square with respect to composition. The second property of this map is that for all psi and phi in the Hilbert space, the inner product of Pm acting on psi with phi, you can actually take the Pm over here, is psi Pm phi. All this follows from the definition. And the third property of this guy is that if you take the P not of M, but of its orthogonal complement, why may we do that? Well, because if M is a linear subspace, which it certainly is, then the complement is a linear subspace, a closed linear subspace. So where I wrote the M here, I could also write the M orthogonal. This guy, of course, goes from H to M orthogonal. And it takes the psi in H to the psi orthogonal we had before. That's a simple consequence. Okay? And fourth, the Pm map is bounded. It's a bounded map from H to M. You remember the symbol for the bounded maps, this curly L. It's a bounded map. And the proof is immediate and will be found on the problem sheet. Okay, so it's not a big thing. Quite interesting is the converse. Quite interesting and heavily used. Is the converse. So, theorem. Let P, not P sub M, but just a P map, that's a bounded map on H. Have the properties first property, P after P is P. Second property, for all psi phi in H, the inner product P psi comma phi is the same as psi P phi. Later on we'll call this self-adjointness, and we will call, equals P, call this the projection property in the self-adjointness. But that will be more subtle. It's simple here, the self-adjointness, because it's defined on all of H. We will come to that. Nevertheless, at this point, we need it like this. Have the properties, then the range, or some people call it the image, of H under of pi, of P, is closed. And the P is the P from before. So you have the P from before, where you have a set down here, where you put a closed set down here. So the range, the image, is of course the P applied to the whole domain. I claim this is closed. And then the P you have must be the P that has been constructed in the way we did in the previous statement. So for any map that's bounded and it has this property and that property, you find a closed subset, namely the range of the map, such that it's the projector to that closed subspace. Okay? So any projector can be written like this, right? So the moral is any projector is the orthogonal projector to some sub-Hilbert space. And the sum is a slight understatement because we even know which one, namely the range of the map. And it's good to practice this, so the proof is on the problem sheet. So this will be quite heavily used. So final section is the Riesz lemma bras and kets. So the Riesz lemma is saying about how you can understand the dual space of a Hilbert space. But let's start differently. Let's say consider a lambda in the Hilbert space. So lambda is usually a complex number. Now lambda is an element of the Hilbert space in this case. So consider lambda an element of the Hilbert space. Then you may define a linear map. Let's call it L sub lambda. It's constructed from the lambda. It takes you from H to the complex numbers in the following fashion. Alpha is being mapped to lambda comma alpha. Well, this is clearly linear, since the inner product is linear here in the second entry. So this is a linear map. It's also a bounded map. How do we find out? Well, we calculate the operator norm of this guy. Do you remember what the operator norm of a map was? It was the supremum over all elements in its domain of the quotient you apply the map, and in the resulting space you take the norm, well, because the complex number is the absolute value, and you divide by the norm of the element. Right? Now this is the sub alpha in H of lambda comma A. Of course, that's what we just defined. Now you know, I'm sorry, and here we have an absolute value. And now we know from Bessel's inequality, nonsense, from Cauchy-Schwarz, we know that this is less or equal to the sub alpha in H, where you take the norm of lambda times the norm of alpha divided by alpha. So this is, of course, just the norm of lambda. But because you have a fixed lambda, this is, of course, less than infinity. Thus, the L lambda is a bounded map from H to C, right? And how do we write this set of bounded maps? We have another name for that. The space of bounded linear maps from H to C? It's a dual space, H star. So again, I emphasize H star is not all linear functionals from H to C, but in the context of Banach spaces and hence of Hilbert spaces, it's only the bounded linear maps from H to C. And I also emphasize, as is shown on one of the problem sheets, that bounded linear maps are always continuous maps as well. Bounded implies continuous. It's actually if and only if. So okay, so that means you can take an element of the Hilbert space and you can construct from it, using the inner product, a bounded linear functional. Big deal. Well, the question is, can any L in the dual space, so can any bounded linear functional from H to C be uniquely written as L is the L of some lambda. So the L sub lambda is the construction we just made. And can any L, any bounded linear functional, be written like this uniquely? And there we have the Riesz lemma, very short lemma. It says yes. Okay? That can be done. And to the yes, there belongs a y, so proof. So let's do this. So we have to find, for any L in any bounded functional, we have to find the lambda that does it. Well, that's one way to show it constructively, and that's what we're going to do. So, however, there are two cases. Case one is that the linear functional we're looking at is the zero functional. What's the zero function? That's the function that sends any Hilbert space element to 0 in the complex numbers. If that is the case, then take lambda to be the 0 in H, and you're done. Because obviously the inner product of lambda being 0, comma something sends everything to 0. So that's the first case. You're done by choosing lambda to be the 0 vector. However, if that is not the case, so if you have a linear bounded functional that's not the 0 functional, what can you do then? Well, then you know that the kernel of this L, you know what the kernel of a linear map is? Okay. Pardon me? Yes, that's the well, I write down, that's the set of all the h's that are sent to 0 by the map, right? So then the kernel of the map, being defined like this, is of course always a subset of the domain, but in that case it's certainly a proper subset, because there are some psi that are not being sent to 0, because otherwise all the psi would be sent to 0, and then this would be the 0 map. Okay? Now the kernel is of course a linear subspace of H. Okay? And in fact, by its definition, it's easy to see it's also a closed linear subspace of H. It's a sub-Hilbert space. So then the kernel is not the entire Hilbert space. But from that it follows that the entire Hilbert space can be written as the kernel of L plus the kernel of L, the orthogonal complement. Why? Well, that's the projection theorem we had earlier. This is closed subset, closed sub-vector space, so it's a sub-Hilbert space. These two together, that's the decomposition we had before, as the whole space, so one sometimes writes in a direct sum here. Hilbert space can be decomposed like this, but because this is not the entire Hilbert space, we conclude that the orthogonal complement of the kernel is not just the 0. It's not just the 0 vector in H, which it would be if it was the entire Hilbert space, because the dual of the entire Hilbert space is just a set with the element 0. Okay, so if the orthogonal complement of the kernel is not only the 0, then we can pick some psi from the orthogonal complement of the kernel and some psi that is not the 0 in H. Why can we do this? Well, because the set doesn't only contain this one. Well, one could maybe be very clear here and say it's more than this, right? So now if you can pick a vector that's a non-zero vector, then without loss of generality, W log, ohne Beschränkung der Allgemeinheit, without loss of generality, can choose the psi to be a unit vector, because if it isn't, you divide it by its norm and it becomes 1. So you see, we have existence of such a vector, and if we're now going to use it to construct something, we better show independence of the choice later on. So there is, whatever we're going to do, there is some well-definition issue hanging over our heads, but we'll clarify that in the end. We just proceed at this stage. Pardon me? Question? Oh, okay. So without loss of generality, we can choose psi to be a unit vector, and then take, remember, we want to provide some lambda that does the trick. Well, in this case, in the second case, we take lambda to be the application of the abstract map that we're given. Now we're given some L in H star. We apply it to the psi. What's the result? Well, it lies in the complex numbers, right? Then we can take the complex conjugate of it, bar, and we can multiply it by the vector psi. And what do we get? Well, obviously we get a vector in the Hilbert space, right? I mean, more precisely, we get a vector in the in the orthogonal complement of the kernel, which is, of course, part of the Hilbert space. Well, we can do this, and why would we do this? Well, obviously because that's our candidate for the lambda we need to prescribe in order to get our L. For then, let's consider L with the such chosen lambda, apply it to some alpha, which could be any alpha in the Hilbert space, and compare the result to if you took the abstract map you were handed. Okay, so if we can show that this difference is 0, we showed that the L lambda map is the L map, which is what we want to show, right? Okay, so let's write this down. What is this? L lambda on alpha. This is, by definition, lambda comma alpha, and the lambda is this one. So it's L of psi bar psi comma alpha minus, well, L of alpha. Now comes the cheeky trick. It's L of alpha times 1. Did I want this? Ah, yes, I do. Yes, okay, good, sorry. Got myself confused for a second. Now, this is just a complex number, right? We can let it jump out, and then we let it jump in again, but to the second slot. So it's psi, L of psi bar, nothing anymore, alpha, minus L of alpha, and we let this one jump into the second slot, psi, L of alpha, psi. Agree? So it changes the bar because here it's antilinear in the first but linear in the second slot. So but now by linearity in the second slot, or additivity in this case, only psi, you have L psi alpha minus L of alpha psi. So again, we emphasize the psi is an element of the orthogonal complement of the kernel. Right? That's where we chose it from. Now, if we could show, so I first claim it and then I show it, if we could show that this is an element of the kernel of L, then I had an inner product between an element of the kernel and an element of the orthogonal complement. So what's the result if that is true? It's 0. So that's what we want to show. So it remains to be shown that this is true. So how do you check whether this is an element of the kernel? Well, you apply the map and see whether applied to this object it yields 0. Well, but because it's a linear map, you can pull this out and you get L of psi L alpha minus L alpha L of psi, all complex numbers, and that is 0. Hence this is an element of the kernel. Hence this is 0. Hence we found the lambda. Well, we didn't find the lambda. We found a lambda because our choice of psi, which we used to construct the lambda, well, it was just some choice in this set. So we need to finally answer the question whether this is a unique lambda we found. We certainly found one, but do we find a unique lambda in H? Or did we find this way a unique lambda in H? And mind you, you could choose the psi differently, but it will always yield the same lambda by the above construction. So let lambda 1, lambda 2 be two such constructed vectors. So that, in particular, L lambda 1 equals L, but the L lambda 2 reproduces the L2. Then you have L lambda 1 minus L lambda 2 applied to some alpha in the Hilbert space. Well, you know it's 0 because the maps both reproduce the same abstract L. But then you have lambda 1 alpha minus lambda 2 alpha is lambda 1 minus lambda 2 alpha. But this is true for all alpha in H. This is 0. And because it's true for all alpha in H, you can conclude lambda 1 is the same as lambda 2. Thus, the whole construction is unique, and the Riesz lemma is proven. Remark. The proof provides for a bijection from H to H star, and because of the construction here, it provides for a linear bijection from H to H star. Okay, so this is why one can say the H and the H star, they're actually the same space, right? They're isomorphic to each other as vector spaces. And so that's this duality. And hence, very often in quantum mechanics, one does the following thing. One says, why would we bother about this complicated space H star if all it is, it's obtained, its elements are obtained by taking an element of H, a unique element of H, and writing down a bracket where the first slot is filled with this element from H, and the second slot is left open so that we have a linear map. So it's a way to think about the H dual of Hilbert spaces that seems to avoid having to understand the H star properly like we did. We did a long time ago, right? So Dirac bra-ket notation. So the whole thing is pretty clear. Since for any element L in the dual space, there exists a unique lambda in H due to the Riesz lemma, as we just showed, such that L of alpha is the same as lambda comma alpha, or what we could also say is L open slot, so the map L as such is lambda comma open slot. So the L acting on something, you leave this slot open here too, you can plug in any element from H, right? So this is then a map from H to C because it can still eat something. Dirac suggested the short notation L equals bracket lambda, and because some people write the inner product not with a comma but with a line here like this, line, and that is it. And British humor has it that because this is a bracket, well actually it's brackets, but well let's say it's a bracket, then most obviously, they say, the first half of it must be the bra. And whatever comes behind is the ket. And they left out a C. Okay? And of course, bra has other meanings too. But you don't want to think too much about this notation because I don't think it's politically correct nowadays. Anyway, so it's the bracket, and you're supposed to write this like that. And there's absolutely nothing wrong with it because of the Riesz lemma. There's absolutely nothing wrong with it. Okay? So far. And he further suggested, so far so good. I'm with him there. So he further suggested to then write, and now it becomes a little funny, to take a lambda in the Hilbert space, and instead of writing the lambda, you already dress it with a ket. So whenever other people, that's us, so whenever we write lambda as an element of H, which is perfect notation, we know exactly what it means to be an element of a set, he suggests that you dress the lambda already with a ket. Why? Well, because he says the whole life purpose of such an element here and such an element there is that they meet, right? Then, hooray, if we have an L and we apply it to a psi, we can write the L like a lambda, say so, and we can apply it to the psi, but if we don't write brackets and just apply it, then the psi looks like this according to the rule, so that's the notation. And then, because quite obviously for some people double lines must become single lines, it looks like this. I mean, this is not so wrong, because it says that if you have an inner product, you can always consider this inner product as the application of the associated functional on the psi in here. Yes, you can. Again, Riesz tells you this is one-to-one. This really fits together. Okay? Now, obviously, one could say, well, it's a little funny that you use half a bracket, whatever that means. Okay, I mean, obviously, it's not half the inner product. It's just a notation. It's a little funny to use it here because this has nothing to do with the inner product. Here it makes more sense because really finding this dual, you need the inner product to associate a dual uniquely with this lambda. Okay, so you see there is, okay, now you might wonder, why on earth would you want to do this? Why on earth would you exchange a beautiful, clear thing, a map that takes an element from the Hilbert space and maps it to a complex number, only because you can due to the Riesz lemma? Why would you interpret this thing, in a sense, always like compulsively as something like this? Well, there is an advantage to it, and that advantage is mainly one that you can memorize formulae more easily. Okay? But that's just for the little people, right? I mean, you don't want to memorize formulae easily, right? You want to memorize them, right? So the question is whether this easy memorizing comes at a cost. Well, it comes at a terrible cost, okay? And so that's why, so the easy memorization thing and is what people would like to get when they use the Dirac bra-ket notation. Well, let me write down a few things. Because we're not going to use it anyway, I just make a few remarks. Of course, you must be able to recognize what people mean, and sometimes you will have to decide, they write down this or that, well, is it this or is it that? And sometimes it's not so clear. So this all is perfectly fine. So there's nothing wrong with it at this point. The gain is that some expressions are quite easily memorized using Dirac notation. So for instance, take this statement that any psi can be written in terms of an orthogonal basis as this decomposition. I mean, this is for advanced students because you have to remember that the psi goes to the second slot. And then this EI here and the EI here. And okay, so, I mean, you memorize this formula anyway. However, if you're inclined to follow this Dirac notation, you say, aha, Hilbert space element, it gets dressed. It was too naked before, it gets a ket. Now you have I in I. Now you say, aha, not a problem. Here you have a bra-ket anyway, so let's write this EI psi. Well, single lines are omitted, first extra rule. And you write the EI here also with a, well, I should actually write it like this, EI psi. You should write you should dress the EI as well. So far nothing has happened because this is a vector, this is a complex number. Vectors are multiplied from the left by complex numbers because you have an S multiplication. Nothing has happened. I only dressed up the whole thing. Well, that is not the big achievement. It goes further. You say, aha, but oh, it would be oh so nice if I wrote it like this. EI, and you put the psi here. Or in other words, you allow the kets to be multiplied also from the right by a complex number. Well, in high school you do this, right? Vector times 2 is 2 times the vector or something like this. Well, we can do this. So we invent an extra S multiplication that acts from the right with the complex number on a vector and yields exactly what the S multiplication from the left yields. Okay? Second extra rule. You have to keep in mind. You see all these extra rules you have to keep in mind in order to make sense out of this. Now it gets a little more interesting because what you do then often is you write this is EI ket bra EI, and you say, well, quite obviously, but I'm not so sure, quite obviously you can take the sum out, you first execute the sum, and then you apply it to the psi. Aha! So what do we mean quite obviously? Because now I first take a sum over half an inner product, and here there's also, okay, so you say, no, we're not that naive. Actually, there's a tensor product involved. Okay, well, let's do that. So you write it like this, which is actually which you will see very often, I assume. This expression you will see very often, that this is written like this. Okay, but remember, up to this point, we already had 3 extra rules. The third extra rule, I tell you now. And that extra rule comes with a sub-extra rule to interpret it. I'm being mean, right? But it's a little like that, right? Okay. I want to make you sensitive for all the extra implicit rules you have. And then the question is, if they're so implicit, why do you have them at all if you don't need them in the first place? But, okay. So the whole thing, one says, is no, it's not that simple or not that naive. What you actually have here, where's the yellow? Oh. What you actually do have here is, I'm sorry. What you actually do have here is you have a tensor product here. They say it's just a suppressed tensor product symbol. Okay, we can live with that. So there was a suppressed tensor product symbol that acts on the psi. Okay, we suppress this. That was the third extra rule. Now, what tensor product is this? Well, this guy here lives in H. This guy here lives in H star. Agree? Because one is a ket and one is a bra. So the whole thing, and certainly the sum, because that's the definition of the tensor product, the sum, this whole element here, is an element of that space. that doesn't look too bad, because that's exactly what an endomorphism is, right? It eats an element from H and produces an element from H, and this is the decomposition. However, usually if you have a tensor product of two maps, F tensor G, then you need to feed it with elements lambda mu, and the definition is that the F acts on the first entry and the G acts on the second entry, and in between here you have a multiplication, okay? Which, if these are maps that send you to C's, the multiplication C and whatnot. So actually we need to submit here not only one element that can be eaten by the second one, but we also need to submit a first argument that can be eaten by the first one. However, there's the sub-extra rule that it's not meant that way, and that you keep the first slot open. So actually the whole thing is meant I in I, EI, tensor, tensor EI. So the whole thing actually keeps an open slot here and then submits the psi in there. Okay, so this is how it is meant if I also make this extra rule. So my counting is roughly about 4.5 extra rules so far. All right? For what? For what? Extra rules just in order to write that the identity on H is I equals 1 to infinity EI, which looks pretty. And you can say, oh, I just inserted the identity in front here. Well, what hasn't been totally clarified yet is how does it work with the infinite sum? Can you actually pull it in and can you pull it out? Well, of course you can. If you think about it in the proper formalism, you can prove all of this. So if these were finite sums, then okay. If they're infinite sums, you need to check anyway. Well, you can check and it kind of works out and so on. But it's a lot of extra baggage. It's a simple notation which looks like, you see, the appeal people talk about, which I fully understand, right? Of course I understand the appeal. The appeal is this eats something from the right, and once it added, it becomes a number, and then you have vectors left. Okay, but please, I mean, is this so difficult, right? And here, and you see here, you submit something which is a ket, and then maybe it comes in a bracket, and it's a mess, right? I find it's a total mess. And there are many other places, if you want to talk about self-adjoint operators, Hermitian operators, and so on. Well, once you know everything is fine, the notation doesn't produce inconsistencies anymore. So if you know that all the objects you use already have all the properties you want from them in quantum mechanics, the notation kind of works. But how do you write down the conditions using this notation? Because what if it doesn't work? Then the notation doesn't work. So then we formulate conditions on our objects in terms of a language that only works if the objects already satisfy the condition. It is all not so good, right? It's all not so good. Nevertheless, it's heavily used, and once you see something like this, I think the best thing to do is to say, well, this is meant in this way, and this is meant in that way, and that is meant in this way, and that is very clear in the first place. So you translate this into that, and you're done, and here we proved all the theorems. Okay? So that's my argument, and here you know the bracket is a linear, is a sesquilinear map from H cross H to C, has these properties, it's continuous, you know what to do with the sum, so you know what this object is. And nobody on Earth knows what this map is. Psi goes to ket psi. What is this, right? This is not a map. This is not something that's happening. What's the meaning of this, right? It's just notation. Why would you do that? Okay? So my point is, yes, this is heavily used in the physics literature. Yes, you need to know how to deal with this. But no, it doesn't clarify things. At the end of the day, it doesn't simplify things. If you're really serious about the formulae and what you're going to derive and prove, it's not making it simpler. It's making it terribly complicated, because why on earth do I need a tensor product with all of this in order to write down something as simple as a basis expansion, right? So this is my little polemics against the Dirac bra-ket notation, which at times it's quite neat to understand. You can insert this, but really, well, if you can prove all the other stuff, you don't need this really. Okay? Good. So did you use that in the experimental part so far? Did you see a bra-ket? No?
Didn't do that much. It was just at the very end of the lecture, a few experimental facts and a little bit of basics.
Okay, good. Okay, so we're still ahead. There's nothing. Well, I mean, there's the problem because I obviously need to provide for the experimental part. I need to provide some theoretical bits, but I'm happy. So far, we're not behind. That's good. Okay, good. So this actually completes our discussion and the techniques that we need to understand Hilbert spaces as far as we need them. What we're going to start next time on Wednesday is we're going to look at self-adjoint operators. And we'll make very clear what the difference between self-adjointness and symmetry is. Symmetry almost looks like it. It's what is usually substituted for self-adjointness on finite dimensional vector space. Exactly the same thing, or for bounded operators. For unbounded operators, like the momentum and the position, and almost any operator in quantum mechanics, if you're not just looking at a spin 1/2 system, right, but any other system in quantum mechanics that's of interest in the lectures, right, harmonic oscillator, hydrogen atom, molecules, whatnot, okay, particle in the well, all of that, they heavily employ unbounded operators, and we need to get self-adjointness under control for all these cases, and we need to get the spectral theorem. We need to understand the generalization of the eigenvalue decomposition that you normally have, right? For finite dimensional Hermitian matrices or real symmetric, it's a real version of that, you can decompose into eigenspaces and you get a diagonalization of an endomorphism on a vector space in a certain basis. In the eigenbasis, it's diagonal and has the eigenvalues on the diagonal, right? But this is only in the finite dimensional case, and it doesn't even suffice, well, it doesn't suffice in the infinite dimensional case, certainly not if your spectrum has a continuous bit, because then the eigenvalues can impossibly constitute a continuum, because your basis is at most countable, so your matrix, if you think of matrices, well, you don't have any, that's the point, but if you thought you had any, they could go on forever. You say, well, that's still countable, right? But the point is you provide lambda 1, lambda 2, lambda 3, lambda 4, but how would you provide a continuum of lambdas, right? You can't. So the mathematics of matrices and projections to orthonormal bases, just thinking of matrices, simply hits the roof. It's not sufficient. It's not the right mathematics, even though it almost looks like it could be, but it's very simple to show that it cannot be the right mathematics. And in fact, we already provide the groundwork to really write down the exact definition of self-adjoint operators, and they will then be decomposed via the so-called spectral theorem. That's the next big goal we have. We'll have to work a little until we arrive there. And that the constructions in there, like these mu measures, these projection valued measures from the axioms of the first lecture, and the P sub A's, the projectors, or the family of projectors associated with the self-adjoint map, they will actually fall out of the spectral theorem. And then we have really all elements together to understand mathematically what precisely these axioms mean, and then we're in a position to tackle all the physics problems. Okay, so that's sort of the first little part of the course is completed at this point. Now we do self-adjoint operators and the spectral theorem. Then we review the axioms, and then we start exploiting all of this for physics. Okay? Thank you.